This is the third video about sections 5.1 and 5.2. Let's quickly review what we did in the second video, although I guess I have to remind you what the lame joke is for today. This is the lamest joke of all. We've done the first two. The third one, the one for today, this video is called the Kid Who Couldn't Stop Saying Strawberries. And so you'll want to probably cover your ears for that one because it is really, really lame. But because of that is why I like it. So what we looked at in the last video was an example that we looked at in the first one, except with a parameter in it. We allowed the a there to be a parameter, and we looked for bifurcations. Just to quickly review what happens, there's certainly a bifurcation at a equals 0. We saw that when a is bigger than 0, that there are 3 equilibrium points. When a is less than or equal to 0, there's just 1 equilibrium point. So certainly the fact that it changes from 1 equilibrium point to 3 as a increases through 0 is the reason that there definitely is a bifurcation value at a equals 0. And actually, many mathematicians would say that's the only bifurcation value. But for us, since we want to distinguish between spiral sinks and sources and real sinks and sources, there's another bifurcation value that can be found by looking at the Jacobian matrix. There's the general Jacobian matrix. And plugging in those two equilibria right there and seeing does the nature of the Jacobian matrix change as a increases through positive values based on thinking about the trace and determinant. And we saw that yes, there was. As a increases, the trace stays at 1, but the determinant increases, and therefore in the trace determinant plane, you're going to cross the repeated root parabola when a is 1/8. When a is between 0 and 1/8, the linear system definitely has a non-spiral source at the origin for the linearized system. The original nonlinear system then has a non-spiral source at those two equilibria, plus or minus square root of a and comma a, when a is between 0 and 1/8. And when a is bigger than 1/8, these become spiral sources, just like the linearized system has spiral sources at the origin for it. When a equals 1/8, the linearized system has a repeated root, and that ends up being like a section 3.5 problem, I think, where you've got a repeated root and you've got one line of eigenvectors. The original nonlinear system, it would be hard to tell, but it would perhaps, I guess I don't know for sure without thinking about it more, have just one, there definitely would be one curve that would be in a sense parallel to the one line of eigenvectors for the linearized system where the solutions are going out. It would be almost straight, though not technically exactly straight. And the other solutions would more closely follow the curving nature of the other solutions of the linearized system. That was quite a mouthful. It's not a real big deal. But that's another bifurcation value, is 1/8. Let's just confirm this, if we can, on the computer, see if it seems reasonable. And I also want to show you that those special solutions that I mentioned that move away from the sources and go toward the saddle point at the origin as t goes to infinity are actually very hard to find. Why don't you zoom in first on the equations. I've got the equations right here. And I plugged in a equals 0.0625, which is 1/16. Can you see that? Okay, so that's a value of a where we should have non-spiral sources at those 2 points that are not, those 2 equilibrium points that are not at the origin. You can't really prove that by looking at this, but you can see that it seems reasonable. In fact, the 2 points should be let's see. Okay. X is 0.25, the square root of 1/16, and y is 0.0625. All right, it's hard to get it exactly there, but we're pretty close. It moves very easily there. Notice the x dt and the y dt over here are very close to 0. We're very close to the equilibrium point up here. And I'll click on it. And, well, it doesn't seem to be spiraling at all if you look at that graph right there. And, in fact, it's not. Just click on lots of equilibrium points near there. There is sort of a spiraling up here, but when you're near that equilibrium point, there wouldn't be spiraling. But what I want you to notice here is I'm going to keep clicking for a bit, get closer and closer to the origin, and I want you to notice that it seems like no matter where I click, it either goes straight up or straight down, practically. It's hard to find that one solution curve that goes away from the equilibrium point in the upper right to the origin. That solution curve definitely exists, but it is hard to find numerically. Probably impossible to get exactly on it. So that's just something that you should realize. I address it in the Mathematica notebooks. Again, technically this is not a separatrix, but it's sort of a separatrix, and they can be quite hard to find. It's hard to get on them exactly unless they're very special, like if they were straight line solutions or something. If I go back down here and change this to something bigger than 1/8, like 0.25 or something, A is now 0.25. Now, technically, there's spiraling going on at the equilibrium point, which would be at x equals 0.5, the square root of 0.25, and y equals 0.25. I'm getting real close right about now. The equilibrium point's right about there. Even here, you really can't see much spiraling. In fact, that doesn't look like any spiraling at all there. Though technically there is going to be a little bit of spiraling around that equilibrium point. In fact, it will, technically speaking, spiral infinitely off and real close to the equilibrium point. But you can't really see that. I suppose that's another good point to make, is sometimes it's really hard to see the spiraling, even though it exists. But once again, it is hard to find that one solution curve that goes directly toward the origin as t goes to infinity. But when you use HPGSystemSolver, you should realize, based on what we know in our heads and thinking about the phase portrait, that it is there. There is a solution that goes from that equilibrium point up in the upper right down toward the origin as t goes to infinity. All right, I think I'm basically done with that example. Let's consider another example. dx dt equals, I'll use a mu this time for my parameter, mu minus y squared, just to do something different. Actually, mu is quite traditional in bifurcation theory. It's quite a traditional parameter to use. So I'm not really bucking tradition. Mu minus y squared for dx dt, and just an x for dy dt. Let's see if we can figure out what the phase portrait looks like for various values of mu, and if there are any bifurcations. First, think about equilibrium points. Set both of these equations to equal to 0, and you see pretty quickly it's pretty easy to find equilibria. X is forced to be 0, and y is forced to be plus or minus square root of mu. At least if mu is greater than or equal to 0. We don't want imaginary equilibrium points, even though we use imaginary numbers in solving systems sometimes. So we've got, when mu is greater than 0, we've got two equilibria at 0 plus or minus square root of mu. When mu equals 0, we do have just actually one equilibrium, just the origin. And when mu is less than 0, we've got no equilibria, 0 equilibria. All right, let's find the Jacobian in general. Again, in these videos, I'm emphasizing using the Jacobian to linearize about an equilibrium point, but I want to emphasize one more time that even though I'm not taking the time to do it, you should make sure you read about how to linearize about a point that's not at the origin using a change of variables to transform the point to the origin in new variables u and v. It's a little bit tricky, but once you've done that, then you can throw away the nonlinear terms for that system, and the resulting linear system in u and v can be studied to determine how the original nonlinear system looks near its equilibrium point that's not at the origin. You should know how to do that. I'm just not taking the time to go over that. What's the Jacobian going to be? Well, the first component of the vector field is mu minus y squared. I differentiate that with respect to x, I get 0. Differentiate it with respect to y, I get 2y. For the second component, the derivative with respect to x is 1 and the derivative with respect to y is 0. So there's my general Jacobian. Is that showing up okay? Maybe I'll try my other black pen and see if it shows up a little darker. That's better. The general Jacobian at one of these equilibria, and I'll sort of do them both at the same time, is going to be 0. If I'm putting a plus minus square root of mu in there, I'll put a minus plus there because I've got a minus sign there. Minus plus 2 square root of mu, 1, 0. The trace here is always 0, no matter what mu is. The determinant is 0 minus this product, which, because of another minus sign, I'm going to get back to plus or minus 2 square root of mu will be the determinant. So for the linearized system in the trace determinant plane, we stay on the d-axis. If mu is less than 0, then we don't even have a point at all because square root of mu will be imaginary. When mu is 0, we're at this point on the t-axis where technically the determinant is 0, and technically that's a case where the eigenvalues of one eigenvalue at least of a linearized system would be 0. And actually that's a non-hyperbolic situation, meaning the linearized system doesn't guarantee anything about the nonlinear system. And in fact, that's even the case when mu is positive. We stay on the positive d-axis. I guess wait a minute, I'm only considering one case here. I'm only considering the 0, 2 square root of mu case for that equilibrium point. This is the way we stay, and since we stay on the positive d-axis, that equilibrium point is always not hyperbolic. Its eigenvalues for its corresponding linearized system are going to be purely imaginary. Think about that for a minute. Try to remember what you learned about the trace determinant plane. The real part is going to be 0. And therefore the linearized system doesn't officially tell us anything about the nonlinear system. For the nonlinear system, you really could get a center or a spiral sink or a spiral source. Now we'll see here in a few minutes that for this particular system we happen to get a center anyway, but it's not the linearized system that guarantees that. For the other equilibrium point, 0, negative 2 square root of mu, that's going to start at the same point on the t-axis but go downward as mu increases in the trace determinant plane. And therefore, once mu is positive, we know it's going to be a saddle point. The eigenvalues will be 1 positive, 1 negative. They won't be 0 or have 0 real part. The equilibrium point right there will actually be hyperbolic. The linearized system will tell us the exact nature of the nonlinear system's equilibrium point there, and it will be a saddle point. So let's quickly see if we can sketch some accurate phase portraits. I guess let's consider the easy case first. Mu is less than 0. That's where we have no equilibria. dx dt is always going to be less than 0 in this case. Mu is less than 0. Negative minus a positive is still negative. The horizontal component of the velocity vector of solution curves will always be negative. Now, it doesn't mean they'll always be constants, and these solutions aren't necessarily straight lines, but the horizontal component will be negative. For the vertical component, the sign will change with x. In fact, there is a y nullcline when x is 0 along the y-axis. Along the y-axis, dy dt is going to be 0, meaning you make little horizontal hash marks. So solutions cross that horizontally. When you're to the right of that, when x is positive, dy dt is positive, so solution curves go up. And when you're to the left of that, dy dt is negative, so solution curves go down. But they're always moving to the left because dx dt is negative. So solution curves are going to look something like this. Will they be parabolas? I don't know. I'd have to think about it. My guess is actually that they won't be, but they kind of look like parabolas. What about when mu equals 0? Then dx dt is negative y squared, dy dt is x. Seems essentially the same. This is less than or equal to 0. It can be equal to 0 when y is 0. The origin is an equilibrium point. Make a big dot there. The vertical y-axis is still the y nullcline. But you do have an x nullcline now. Where y is 0, the horizontal x-axis is going to be an x nullcline. So you make little vertical hash marks there. Now, dy dt still is equal to x, and dx dt is always less than or equal to 0, so if you think about this a little bit, you realize solution curves have to look like this. Now, I'm sort of skipping the step where I draw in those northeast, northwest, southeast, southwest kind of arrows. But if you do that, and think about it a little bit, you realize that the solution curves will have to look like this. And I guess down here they'll cross here before they go around the equilibrium point. Kind of strange, but that's what it's doing. And this equilibrium point, if you think about it, it definitely is kind of unlike anything that we've seen before. I guess it's sort of like a half saddle. There does have to be one special solution that goes straight toward it as t goes to infinity, and one special solution that goes straight toward it as t goes to minus infinity. It might be getting hard to see here. But when solutions come close, but underneath it, they just stay underneath, sort of like a saddle point, but on top, they're kind of like a center. They kind of go around it. So it's sort of like a half saddle, half center. Remember, the linearized system had 0 as an eigenvalue there, and is not predictive of necessarily of the type of equilibrium point we would have here. All right, now the more interesting case, what about if mu is positive? Mu is positive. There we have our two equilibria. And we already found the linearization about those. The y-axis is still a y nullcline because that second equation is not changing. What about the x nullclines? Well, if mu is positive, they'll be at plus or minus square root of mu. Set this equal to 0 and solve for y. Plus or minus square root of mu. There will be two of them, where the vector field is vertical. And therefore, where blue and red cross, there will be equilibrium points. There are two equilibrium points. Thinking about signs, let me draw some arrows here. Let's first think about dy dt. That's going to be positive when x is positive and negative when x is negative. So we definitely have upward pointing arrows in these regions and downward pointing arrows in these. And then thinking about the first equation, dx dt is going to be negative when y is close, when y is big, either positively or negatively. So up here we point to the left, and down here we point to the left. But if y is close to 0, between plus and minus square root of mu, then dx dt is going to be positive, and here we'll point to the right. This point, recalling our linearization and our trace determinant plane for that, that point that was below the axis is going to be a saddle point when mu is positive. Thinking about the directions of these arrows, there's got to be a solution curve that heads straight toward it. I'm drawing it like it's a straight line, but it's not necessarily straight. Don't let that deceive you. There'd have to be one going away from it. Again, I'm drawing it straight, but it doesn't necessarily have to be straight. In fact, I'm pretty sure it's going to curve. How it curves is not so clear. I'll just draw it straight for the moment, but keep in mind that a more accurate picture is possible, and maybe if I have time, I'll look at the computer. In here, you've got to go like this, thinking about the arrows, and this is a saddle point. Up here you're going to go like this, and down here, over here you're going to go like that. These two have to be pointing toward this point, and these two have to be pointing away. Now this one had eigenvalues based on the trace determinant plane that were purely imaginary. The linearized system did. So for the linearized system, the point was a center. Now again, that doesn't guarantee this one's going to be a center, but in this particular case, it does happen to be. There are going to be some ovals around this thing that are going to be solution curves. They're going to be periodic solutions in this range here. And in fact, this one particular solution that goes away from this point down here is going to end up coming back around to the same point. That makes this point something called a homoclinic point, where one solution curve goes away from it and comes back to itself here. And again, there are periodic solutions in here. They're not circles, and maybe they're not even ovals perfectly, but they're kind of shapes similar to that. And finally, you're also going to have solution curves out here that, if you think about it a bit, are going to do this kind of thing. Now, a couple things. you should be able to draw this and fairly quickly, like I did here, based on these nullclines and linearization. You wouldn't necessarily know without further knowledge that we definitely have periodic solution curves in here that close up on themselves. That would require a little bit more knowledge. This system happens to be something called a Hamiltonian system, which is the subject of section 5.3. And it's got, as a Hamiltonian system, something called a Hamiltonian function. And the level curves of that function of two variables, it'll be, we'll call it h of x comma y, are going to end up being the same curves that the solutions lie on top of. What does the Hamiltonian function happen to be here? Let's see, I did it before I came here. I think it's going to be 1/2 x squared plus mu times x minus, no, mu times y, excuse me. No, I think I want a minus sign there. Minus mu times y, and then plus 1/3 y cubed. This is actually a function of x and y, but I'm going to put the parameter in there also. And think of it as a function of its variables and the parameter. And if I do a contour plot for, say, a specific positive value of mu, like 3, I should see a picture that looks similar to what I have on the screen, except there won't be arrows on it. All right, somewhat similar. Let me plot more contours by adding the command contours, and well, let's put like 50 of them in there. That's better. Can you zoom in on that? That's a more accurate picture of the shape of the solution curves, but you should be able to see that the saddle point is right about there. It's not drawing in the one line, a curve that goes toward that as t goes to infinity, or goes toward it as t goes to minus infinity, but they would be there. They're not technically straight, but they kind of look like they might be almost straight. There would also be this solution that makes that a homoclinic point, and it's a homoclinic orbit going around over here and coming back. And you can see these sort of oval things are curves that solution curves lie on also. And there's the other equilibrium points right up there. How did I come up with this? I'm not going to tell you. Something, if you're interested in reading section 5.3, you can read about. Or if we get there, we'll do that. But that's a little bit of extra information that shows how, even though the linearization doesn't quite give you what you hope for in that case of the equilibrium point that's above the axis, it can still be proven to be a center anyway. In this case, that's definitely not always the case. Well, let's animate this a little bit. I better have fewer contours though, so it doesn't take too long. Okay, this is what it looks like when mu is less than 0. We'll see if we can see the bifurcation. I'll set it in motion. Mu starts at a -3. Now mu is increasing. There we go. When you pass through 0, a bifurcation occurred. Ignore the fact that those curves look kind of jagged. They're not really. They are more curvy. I think the performance goal quality might make this better. I think this is going to make it smoother. But it goes a little slower. There we go. You can see that better now. Okay, so that's illustrating. A bifurcation occurs at mu equals 0, and actually there's going to be no other bifurcation point as mu continues to increase. Those equilibria are just going to move further and further apart. Guess we're running low on time. I'd like to end this then with a joke. So if you just were scared off by the first two, now's the time to end it. Because now we're talking about the boy who couldn't stop saying strawberries. All right, this boy was sitting in his home one day. His mom was doing the dishes. He cut his finger and said, strawberries. And his mom said, "What did you say? Get out of my house. I never want to see you again." The boy was kind of flabbergasted, but he obeyed. Left the house, started walking along the street. He said, "Strawberries," as he was walking along, just depressed about what had happened. The mayor of the city happened to be driving along as he said this, had the window open, and heard him and said, "What did you say? Get out of my city. I never want to see you again. Don't ever come back." And so he left the city, ended up in the state capitals walking along, and said strawberries as the governor's car happened to be going by. The governor, of course, said, "What did you say? Get out of my state. I never want to see you again." I happen to be living fairly close to Washington, D.C., and so he's walking along in Washington, D.C., and he says strawberries as the presidential motorcade goes by. The president hears him and says, "What did you say? Get out of my country. I never want to see you again." So he hops the next plane to France. He's walking along in France, and this person sees him and says, What's wrong? And he says, "Well, I said strawberries, and my mom, my mayor, my governor, and my president kicked me out of home, city, state, and country." And the Frenchman says, "Well, what's the problem here? That's not a big deal. Why don't you just go explain that you didn't mean anything by it? I'm sure they'll let you back in." So he goes back to America, goes to Washington, D.C., meets with the president and says, "Please, Mr. President, it's only a fruit. Can I please come back in the country?" And the president says, "Oh, okay, I feel like being forgiving. You can come back in the country." Goes back to the state, talks to the governor, says the same thing. The governor says, "Oh, I guess you can come back in my state." Goes back to his city, says the same thing to his mayor. The mayor says, "Oh, I guess I'll accept you back in my city." Goes to his house, talks to his mother, begs, pleads, "Mom, it's only a fruit. Can I please live back at the house again?" The mom is a little concerned, but decides, "Okay, yes, I guess you can live in the house again. You can be my son again. Oh, by the way, can you go get some milk? Here's some money." So the boy crosses the street to go get some milk and promptly gets hit by a car and dies. What's the moral of the story? Look both ways before you cross the street.